You've seen the images. We've all seen them, right? These incredible pictures AI can create now, sometimes like hyper-realistic, other times just completely wild.
Oh, absolutely. The speed of progress is just staggering.
It really is. And, if you've been following this space, the top image generators have mostly been, well, one of two types. You've got diffusion models.
The one's known for amazing quality.
Exactly. And then the autoregressive models, kind of borrowing ideas from those huge language models everyone talks about.
That's right. Diffusion models, yeah, fantastic quality, but training them, generating from them,
Yeah.
it could be pretty heavy, computationally speaking. All those steps, cleaning up the noise.
Right, that iterative process.
Yeah. And autoregressive models, they can be quicker, building things up piece by piece, like predicting the next word.
Makes sense.
But they've often worked with discrete versions of images, which sometimes maybe limited the absolute finest details, the fidelity.
Okay, but there's this other way, isn't there? A technique that's been around, maybe not grabbing the headlines lately, but it could offer a totally different route to these high-res images.
You're talking about normalizing flows.
Exactly, and that's what we're diving into today. We found this really fascinating new research paper introducing something called STARFlow. And this model, it's taking normalizing flows and basically showing they can compete, play in the big leagues of image generation.
It's a really interesting development. Normalizing flows, they're likelihood-based models. They learn these invertible transformations.
Invertible, meaning they can run forwards and backwards.
Precisely. They learn to map complex data, like your image, to a simpler distribution, think like a standard bell curve, a Gaussian, and crucially, back again.
Okay.
And because it's invertible, you get this exact mathematical measure of how likely your data is, which is great for training. And it all happens in continuous space.
Right.
Unlike some models that have to sort of discretize the image data first.
But scaling them up has been the problem.
Historically, yes. Getting them to work well on really big, high-resolution images was seen as a major challenge.
Right. So our mission for this deep dive is to figure out how STARFlow actually solved that. What is this thing? How did they make normalizing flows scale like this? What were the clever tricks, the specific innovations? And, what does it mean for the whole field? Is this a new major player? Think of it like uncovering this, hidden trail that suddenly turned into a superhighway for making images.
That's a good way to put it.
Okay, let's get into it. So we had diffusion, great quality, maybe slow, autoregressive, maybe faster, sometimes tricky details, and then normalizing flows. These nice mathematical properties, but scaling issues.
Right.
The paper mentions previous work, things like TARFlow, starting to mix flows with transformers. But the big question was always hanging there. Can they really scale? Can they compete on big, complex images?
And what's so compelling about the STARFlow paper is it basically shouts, yes. It's really the first clear demonstration that, look, these normalizing flow models can be scaled effectively for high-res, large-scale image modeling.
Wow.
And they're getting results that are genuinely competitive with the state-of-the-art diffusion in autoregressive models.
So it wasn't just luck. They had some reason to believe it would work.
Exactly. They didn't just stumble into it. They built on a solid theoretical foundation.
Yeah.
There were results showing that certain types of autoregressive flows, if you make them deep enough, specifically with more than 2 layers structured in a certain way, they become theoretically powerful enough to approximate any complex distribution, like the distribution of natural images. They're universal approximators.
So the theory said it should be possible.
Pretty much.
Yeah.
It gave them the confidence that scaling these models wasn't a dead end, that the fundamental capacity was there if they could just figure out the right way to build and train them.
Okay, so theory gave the green light. How did they actually build it? What were the big breakthroughs to make it work for high-res images?
Well, they introduced a few really key innovations. The first big one is architectural, something they call the deep shallow architecture.
Deep shallow. Sounds intriguing.
Yeah, so instead of spreading out the transformer layers evenly through the whole model, like you might expect, they found it's way more effective to pile most of the computational power, most of the parameters, into the very first block of the flow, the one closest to the simple noise distribution you start from when generating.
So front-loading the complexity.
Exactly, that's the deep block. And then it's followed by just a few shallow blocks, much simpler ones with fewer layers.
Why does that work better? It seems counterintuitive almost.
Well, their experiments showed that's where the most important computations were happening during training anyway. It just sort of emerged.
Yeah.
The intuition they offer is pretty cool. The deep block acts almost like a Gaussian language model, figuring out the high-level structure, the semantics of the latent representation.
Okay, like the main ideas of the image.
Right. And then the shallow blots come after, and they act more like a learned image tokenizer, computationally lighter, just refining the finer details, the textures.
That makes sense. Any other benefits to that design?
Oh, yeah. It simplifies things like conditioning the model, say, on text. You really only need to feed the condition into that main deep block.
Ah, less work.
And interestingly, it potentially allows you to initialize parts of that deep block using pre-trained language models, which is a neat link. Plus, it actually makes inference generating the image faster compared to a model where the layers are spread out evenly.
Okay, deep shallow architecture, that's one. What else did they figure out?
The second huge piece is learning in latent space. Trying to model, a 522 by 512 image directly, pixel by pixel, with a normalizing flow, that's incredibly hard, just computationally very, very expensive.
Yeah, that's a lot of data points.
Exactly. So STARFlow does something smart, borrowing from models like Stable Diffusion. It doesn't work on the pixels directly. It works on a much smaller, compressed version of the image.
The latent representation.
Precisely. They use a pre-trained autoencoder, kind of like the one in Stable Diffusion, to squish that big image, say 256 by 256, down to a much smaller grid, maybe 32 by 32 numbers.
Okay.
And that's what the autoregressive flow learns to model, this compressed latent space.
So the flow's job gets much easier.
Way easier, though there's a key detail. They found adding a little bit of random Gaussian noise to these latents before training the flow was really important for stability.
Interesting.
And then, crucially, you need to get back to a full image, right? So they also fine-tune the decoder part of that autoencoder. They teach it how to take the latents processed by the flow, including that bit of noise, and turn them back into sharp, high-quality images.
Got it. So encode, add noise, run through the flow in latent space, then decode and clean up.
That's the gist. And the paper really emphasizes this is way more effective for high-res images than trying to model pixels directly. The flow becomes this powerful engine for understanding the structure within that compressed space.
Makes perfect sense. Okay, so deep shallow architecture, learning in latent space. What was the third leg of the stool?
The third key innovation is a novel guidance algorithm, specifically for classifier-free guidance, or CFG.
CFG, that's everywhere in text-to-image now, right? Helps make the image match the prompt better.
Exactly. It's super common. It basically works by amplifying the difference between what the model predicts with your text prompt and what it predicts without it, sort of pushing it harder towards the prompt.
Like giving it a stronger hint.
Right. But previous attempts to use CFG with normalizing flows, like in that earlier TARFlow model, they used a simpler sort of linear approach. And the STARFlow team found that could get unstable, especially if you crank up the guidance strength, use a high CFG weight, which you often want for really good text-to-image results. The images could degrade.
Okay, so the old way wasn't quite cutting it.
Yeah. So they went back to basics, looked at the math behind guidance, and derived a completely new formula, one that's specifically designed for their model, particularly how that deep block operates in the Gaussian latent space.
Tailor-made guidance.
Pretty much.
Yeah.
And they added a little trick, clipping a variance ratio just to keep things numerically stable when the guidance is strong.
And did it work? Is it more stable?
Massively so, based on their results. They show this new guidance approach stays stable and maintains high image quality over a much wider range of guidance weights.
Which is crucial for getting those really strong text-to-image generations.
Absolutely. It's a key piece for making the whole system perform well on that task.
Okay, wow. So these three things together, the clever deep shallow setup working in latent space and this new stable guidance that's the magic sauce, how does STARFlow actually perform when you put it all together? Does it really measure up?
Well, connecting it back to that big picture question, the results they present are pretty compelling. They really do show that normalizing flows are, genuinely competitive now.
Okay, like what metrics are we talking?
They report competitive FID scores. That's a common metric for image quality on standard benchmarks like ImageNet at both 256 by 256 and even 512 by 512 resolution.
512, okay. That's pretty high res.
Definitely. And for text-to-image generation, using the CoCO dataset, which is quite challenging, their zero-shot FID scores are right there in the mix with the top models. They even note the perceptual quality seems to be approaching the leading diffusion models.
So the numbers look good. What about just looking at the pictures? Do they look good?
The examples in the paper are impressive.
Yeah.
You see high-resolution outputs, lots of diversity in the content, handles different aspect ratios, which is nice.
Yeah, that's useful.
And the quality, perceptually. Yeah, they describe it as comparable to the other leading methods. You see sharp details, coherent scenes, good response to complex text prompts. It definitely looks like it belongs in that top tier now.
Okay. And what about speed? Efficiency? That was potentially an advantage for flows, right?
It is, theoretically. Generating an image with a flow is generally a single pass through the model blocks, unlike diffusion with its many denoising steps.
Right.
And that deep, shallow architecture they designed, that specifically helps speed up inference for STARFlow.
So faster than diffusion.
The paper shows significant speedups over diffusion, especially once you get past tiny batch sizes. Now, compared to all autoregressive models, it might depend on the specifics, but it's definitely faster than the diffusion process.
Okay. Competitive quality, decent speed. Can it do more than just generate images from scratch? That invertibility you mentioned earlier sounds useful.
Absolutely.
Yeah.
And they demonstrate a couple of cool applications stemming from that. First is training-free image inpainting.
So filling in missing parts of an image.
Exactly. And training-free is the key. You can just take an image, mask out a region, encode it into that latent space. The masked part basically becomes noise. And then you use the flow, sampling iteratively just within that noisy latent region, to fill it in naturally, guided by the surrounding latent information. No extra training needed for an inpainting model.
That's pretty neat. Saves a lot of effort. What was the other one?
Interactive image editing. This one does involve some fine-tuning, but it's powerful. They trained STARFlow for text-guided image editing, like change the dog's fur color to brown.
Okay.
Because the flow is invertible, the workflow is potentially really smooth.
Yeah.
You take your source image, do one forward pass to encode it into the latent space.
Right.
Then you apply your edits, guided by the text within that latent space using the flow, and then you do one reverse pass to decode the modified latent back into the final edited image.
Oh, single pass encode, single pass decode. That sounds much faster than some other editing method.
Potentially, yes.
Yeah.
It integrates really elegantly with the whole Transformer Flow architecture. It could lead to much faster, more interactive ways to tweak and modify AI-generated or even real images.
Okay, so it sounds incredibly promising. Competitive quality, good speed, these unique editing and inpainting abilities. But nothing's perfect. Are there limitations? Things they still need to work on?
Oh, for sure. And the researchers are upfront about it. One big one is that reliance on the pre-trained autoencoder.
Right, the thing that shrinks and expands the image.
Exactly. Training the autoencoder and the flow together, end-to-end, is still future work. They also mentioned that while it's faster than diffusion, inference speed could probably be optimized even further.
Makes sense.
And, most of the testing is on standard image benchmarks, seeing how well it generalizes to really diverse, out-of-distribution data, or maybe even other things like video. That's still an open area for exploration.
Gotcha. And thinking bigger picture, what are the potential impacts here, good and bad?
Well, on the plus side, things like that, fast, interactive editing and the quality generation, could be amazing tools for artists, designers, maybe assistive tech. It offers a different kind of creative control.
Yeah, I can see that.
But the flip side, of course, is that any powerful image generator makes it easier to create realistic fakes, misinformation.
Sure.
And the interactive editing could potentially make that process even faster or easier. So they rightly stress the need for things like watermarking, ways to trace where generated content comes from, developing those tools alongside the generation tech itself.
A familiar challenge in AI right now. Okay, so wrapping this deep dive up, STARFlow feels like a really significant step. It's basically proven that normalizing flows can scale, they can produce high-res images, and they can compete with the big dogs like diffusion and autoregressive models.
Yep, thanks to those clever innovations, the deep shallow design, using the latent space smartly, and that custom-built guidance system.
It puts normalizing flows firmly back on the map as a serious contender.
It really does. Changes the landscape, potentially.
Which leaves us, and you, with this final thought to chew on. Given STARFlow's specific strength, that invertibility, that ability for single-pass encoding and single-pass decoding for editing, how might that specific feature change how we actually work with AI images in real time? Like for creative workflows, design, art, maybe even animation, what new ways of interacting, what new tools could emerge from that capability, things that other models maybe can't do quite as easily or quickly right now?
It definitely suggests some new possibilities are on the horizon. It could be very interesting to see what people build with it.